first organometallic compound, so that will be called as a organomagnesium. This is the structural representation of your reagent, where we can use the R. Instead of that R, you can use the alkyl group. You can use where R is equal to, you can take any example. Okay, R means alkyl, allyl, vinyl, propargyl group. Okay, then benzylic, then phenyl, whatever type of R is there, all types of organometallic compounds are available. Okay, so okay, we can prepare it now. So basically, so first of all, that organometallic compounds in the where magnesium is there now. So here carbon magnesium bond is polar. Example, how much it is polar now? It depends upon the electronegativity. Example, here carbon is negative and this will be a positive. So the difference between this carbon is 2.5 and magnesium is 1.2 now. So difference is 1.3. So the difference between this two is 1.3 now. So on the basis of the difference between the electronegativity, so we are decided the reactivity. So organometallic compounds, example, magnesiums are highly reactive. Generally, they are what? Highly reactive. Okay, and violently react with water or violently react with oxygen. That's why whenever we are using, whenever we are work on it, so always remember or always keep in mind. So we should maintain the anhydrous and dry environment. So should maintain anhydrous and dry. Okay, that means absence of oxygen. So this reagent is widely used in field of what organic synthesis as act as a base or act as what nucleophile. Now, so the second important task is what the organomagnesium compound. Generally, what these compounds are used in dry ether. So the solvent which is used for the organomagnesium is a dry ether. Now is a dry ether. Now you know that ethers are generally diethyl ether. This is the structural representation of what ether now. And here this RMgX. Now here magnesium is going to be positive charge now. So as we'll discuss already in the structure. Here look at this now. What is the role of what ether now? So this lone pair on the oxygen from that ether is going to stabilize that magnesium positive ion. Okay, is going to stabilize the. So this type of the complex is going to be formed now. And here this carbon is going to be negative charge, so it will be act as a nucleophile or act as a what the base now. So this is a highly reactive compound. Okay, that means highly polar. So from that 1.3 we have decided that it is highly polar and highly ionic. Okay, so it is based on that 1.3 now. So it's highly reactive, it's violently react with water and oxygen. So well, that's why it should maintain the anhydrous condition, dry environment. And so for that purpose we are going to use the ether as a solvent. We have this ether example is diethyl ether. So we have the examples are AT2O, then we have the example is THFN, etc. etc. Okay, this is the what the introductory part about the organomagnesium. Now this reagent is firstly prepared and widely used nowadays widely used in organic synthesis for the purpose of what CC bond formation. You know that organometallic compounds are used for two purposes. Organometallic compounds are used for the two purpose. One is example the purpose of what using the organometallic compounds is making carbon-carbon bond by developing carbon-carbon bond and for the abstraction of the proton. For the abstraction of proton. So these are the two important uses of what the organometallic compounds, because it have the carbon and it will be react with another deficient carbon, so it will form a carbon-carbon bond. So the purpose of what organometallic compounds are for the making carbon-carbon bond as well as for the abstraction of the proton. Okay, so we have the first reagent, that is organomagnesium, and structurally it is what RMgX. You can use R, where R is nothing but the, we can use anything, that is R is equal to what alkyl group. You can take methyl, ethyl, propyl, whatever it may be. We can use the alkenyl group. Okay, we can use the alkynyl group. We can use the phenyl. We can use the benzyl. We can use vinyl, then propargyl, etc. That means all type of what R can. So here the applications of what this organometallic compounds. Now example organomagnesium application. So application in terms of what how it will be worked now. Okay, the first of all because of that negative charge which is developed on the R, so this reagent is a good source of all the base. That means first of all it act as a base. Act as a base. That means this reagent is going to be act as a base. You know that what is meant by base now? So this type of the chemistry is there generally. That's called the acid-base reaction. where base is going to be take the deficient proton. So this is called the example. This is deficient hydrogen. Okay, and here it must be electronegative atom is there now. So that hydrogen is going to be abstracted by the base, and it will form the R negative ion, and finally what BH is going to be developed. So here uh, Grignard reagent is one of the stronger base. It abstracts the proton even from least acidic center. What happens when this Grignard reagent is going to be react with water? Yes, what will be the answer? That means if water is there, then your reagent is completely destroyed. That's why we always try to avoid that water and what oxygen contact with the magnesium. Water is a neutral compound. Water is a neutral, but still your R negative is going to be react with water. That means you can think on it how it is a reach now. So it will take the proton from that your water molecule, and so something is product is developed. Like example here like this. So that means the resulting product is hydrocarbon. By the abstraction of the proton by your reagent, so resulting products are hydrocarbon. That means it abstracts the proton even from least acidic center, example water. So water is a neutral. So from water also it will take the proton. Now that's why it is much more base. It much more basic one. Okay. Now we have the applications example. I have the flow chart example. This is what RMgX, and that RMgX is going to be react with various example. We'll take the example. So here this is what water suppose. This is what the deuterated water. This is one example is phenol. Another example is here example amide. One more example is there, that's called the carboxylic acid. Okay, so this is what centrally located your reagent, and it reacts with various reagent. Example, first of all water, the next is D2O, that is deuterated water. Then example is what alcohol, so we'll take that example is ROH. Then we have phenol is there, that is AROH. The next example is what your amines, RNH2. Then we have example is RCONH2. We have alkynes example RC triple one CH. Okay. We have the one more example is sulfonic acid, that is RSO3H. We have one more example is RCOOH. Okay. Then let's take the example. Now, what are the products are expected from all these reactions now? Okay. So carboxylic acid, from alcohol, from phenol, from water, all are the acidic hydrogens are there now. So some examples like amines. Amines are generally basic, but you know that the lone pair is there now on nitrogen. So due to that reasons, it will take the electron from hydrogen also. So the hydrogen becomes a deficient. So likewise, so find out the expected product of all the compounds. We have next example is substituted phenols are there now. You know that the compounds of benzoic acid, that is ArCOH. Take this example. Now the products are all will going to convert into the hydrocarbon. Example, this is R, which is from your reagent. This is your R. Okay, this is the R, which is from your reagent. And now that reagent is going to take the hydrogen from your reactant. So here it will become say converts to RH. It will become say RD. It will become say RH. It will become say RH. It will also become say RH. Here also the RH. This is RH, 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 and RH. That means when the Grignard reagent is act as a base, so it will be converts into the hydrocarbon. Okay. And what are the byproduct is going to be developed now? Here byproduct is in all the cases the byproduct is what? Here MgX is common. So here MgX is going to be bind with the OH. Here MgX is bind with OD. Here Mg is bind with the OR. Here MgX is bind with the OAR. Here this is what MgX is bind with the NHR. Here this will be what MgX, and this will be what NHC, etc. etc. All are the required, all are the remaining products are there now. So basically, what in all reactions, we'll simple think on it. So basically, here this reagent is act as a base now. This will be acts as a base. So it will be abstract the hydrogen from the, if no electrophile is there, then it will be just work as a base now. Okay. The next applications of your particular reagent. Example, what happen when we have two halogens are there now. So let's look at the example fluorine, and here iodine is there, and I'm going to react. I'm going to react with the magnesium in dry ether, and the next reactant is RCOOH. So what happened with this now? So here where the magnesium is going to be insert now, which bond is going to be more polar now, whether carbon fluorine or carbon iodine? So here
Carbon
first of
fluorine.
all,
Carbon fluorine.
carbon fluorine is going to be a more polar. Okay. Now the question is that, so displacement of fluorine by the magnesium is very difficult now, and that's why in the preparation also what so here this is the preparation or preparative method now. Generally halogens are used as a chlorine or as a bromine now, or as a iodine. So fluorine generally cannot be used for making the organometallic compounds now, because it's difficult to break that bond, and insertion of that magnesium is very difficult now. So higher the size of a halogen atom, that will be the easier one to insert that magnesium. Now here magnesium is going to be insert in between the carbon iodine bond. So here we'll develop the organometallic compounds. Look at this one. So fluorine is intact here, and here I am going to develop the organometallic compound of this one. Okay, this is the compound which is going to develop now. Now the second one, the RCOH is given now. Second one is what? This is what the fluorine, and here this is what MgI. Now how this RCOH is going to react now? Now RCOH having acidic character, and this magnesium is negative one, so it will take the proton and it converts into the hydrocarbon. So what will be the product now? Here this will be the hydrocarbon, and the byproduct is MgI and OCO. So from that reaction we can conclude that the magnesium containing reagents, that is organometallic compounds of magnesium, are going to be act as a good base. They will abstract the hydrogen and converts into the hydrocarbon. So halogen containing positions are going to be converts into the, look at this position now. Here iodine is there now, and here hydrogen. This is the first application of an organometallic compound as organomagnesium. Now the second one, which is very important, that is acts as a nucleophile, because carbon is rich, so it must be react like any nucleophile. Okay, so first of all we'll discuss about the that this R negative is generally what, that as I already discussed, this R is negative charge, so it must react with the electrophile now, and that's why it is a what will be the reaction is there now. Look at this one. This is example, my reagent, that is RMgX, is going to be react with the any electrophile. Electrophile must be a deficient, and here there will be a new bond is going to be developed now, like this. Okay. Similarly, now we have various applications are there, particularly for alkyl containing the reagents. Okay. So alkylation is generally going to be takes place on polar organic functions now. Now, which are the polar organic functions now? You know that there is a one simple molecule, that is what, carbonyl group, that is aldehyde. When aldehyde is going to be react with RMgX, aldehyde is a polar, and we are going to bind that polar group with the, so in the first step this will going to be developed now. Look at this one. This R negative is going to react with electrophilic center, example carbon. This will be electrophilic center now, and this will be the negative center. So this bond will be open toward oxygen, and here I am going to develop the new bond, that is one, this, and this will be MgX. Finally, with the help of a protonation in the second step, always remember protonation never be done on first step. Either your reagent is first react with water. Okay, so this should be a keep in mind, and here you will get the alkylated product now. This is called the alkylation of polar function group. Okay, and all the polar molecules are going to be alkylated. Here R is going to be alkylated on the particular carbonyl compound. So if I take the simple example of SN2 reaction, suppose example I have this methyl bromide as my electrophilic one. So as you know that this R is nucleophilic partner, this will be the this will be the one, the deficient partner. The reaction very simple, like SN2 process, and it will be going to convert into the RCS3 now. This is called CC bond formation reaction, and here the byproduct is like this. So that's why this organomagnesium compounds are act as a the nucleophile. So we have various examples are there. So let's look to the flow chart. RMgX. This is my starting material, and when the starting material is going to react with my particular example, So find out the product of these two reactions. Here the first example is for formaldehyde. Next example is what your acetaldehyde or simple aldehyde, and next example is what ketone. So very simple reaction is this. Here this R negative is going to be react with the carbonyl carbon. Here the carbonyl carbon, here the carbonyl carbon, or other electrophilic one, and the reaction will be going to like this one. So this H.
First case में primary.
Now the synthesis of different types of alcohol is going to be take place with the help of what your organomagnesium. Okay. Now, so sometimes the question is there now. We can take the various examples of what carbonyl compound of aldehyde. We can take benzaldehyde, benzophenone, acetophenone. So various carbonyl compounds are there now. Always keep in mind carbonyl carbons are electrophilic in nature, and we are going to react with R negative from the reagent. So this R negative is going to be combined with carbonyl carbon and bond will be open. So this is example of nucleophilic addition reaction. This will be called as a nucleophilic addition reaction. And in nucleophilic addition reaction, your previous carbon is the sp2 hybridized, and sp2 hybridized carbon is going to convert into the sp3. That's called the nucleophilic addition reaction. We are going to add the nucleophile, and sp2 converts into the sp3. So this is the first application where we can convert the carbonyl compounds to the alcohol. Okay, so we have different types of carbonyl compounds also there. Now what about the conjugated chemistry now? So here this is my reagent, that is RMgX. This is my reagent. Okay, and now that reagent is going to be react with the two types of reactant. Now example, the conjugated molecules. Conjugated molecules are example this one. Okay, Grignard reagent, that is R negative, always show the 1-2 addition reaction. Always. What is 1-2 now? It only react with the, so this negative charge is going to react with the carbonyl carbon, and here this will be the O negative. Here bond is intact, and this will be my R. This is called 1-2 addition reaction. And now when the protonation is done now, so it will be converts into the tertiary allylic alcohol. Okay, this will be formed, and you know that this type of the molecules are generally used in the various name reaction, etc. The product of this reaction is used in the name reaction. So this is called 1-2 addition. But is it possible to show the Grignard reagent 1-4 addition, or Grignard can show the conjugate addition in the simple condition? No, Grignard never show the 1-4 addition reaction. But if copper is there, or any copper containing salt is there, so then it will be converts, or it will be react with the fourth position. Here the reaction will be like this, but in this case the reaction will be proceed onto the fourth position. Where the fourth position? 1, 2, 3, and 4. And here by reacting with the fourth position, so you will get the this type of your compound, and by the protonation it will be converted to enol, and you know that enol is going to convert into the ketone. Now look at these two reactions. Both reactions are different. In first reaction, your double bond is intact. In second reaction, carbonyl group is intact. So that's why this is called as a 1-2 addition reaction, and this is called as a conjugate or 1-4 addition reaction. This will only happen when copper is there now. This is what only happen when copper is there. Now second task is what? If there is a crowding, at the alpha position. What is alpha position now? Alpha position is nothing but this one. This is alpha and this is beta. Okay, so if there is a crowding at alpha, for example, this is what phenyl ring is there. Now this phenyl ring makes the crowding at the C2 center. That is basically your nucleophile is very difficult to approach there. Nucleophile is that means it's very difficult to approach on the second position. Then at neutral condition, that is RMgX is going to react like this one. That is conjugate additions can be possible. That means there are two ways by showing the conjugate addition. One is the presence of copper. So 1-4 addition is only done. 1-4 addition is only done by the two way. One is the copper is there, and second is a crowding at alpha position. Crowding at which position? Alpha position.
Alpha.
So if the crowding is there now at alpha position, then and then only your nucleophile is going to react at here now, because at this position it's very difficult to attack. Okay, this should be very keep in mind now. It's a very important application. Okay, so I have one example. So this is what cyclohexenone, and cyclohexenone are going to react with the two reagents. One is methyl magnesium bromide in combination with simple water. This is MEMgBr, my first reagent. My second reagent is what? H3O plus, and here this is methyl magnesium bromide in combination with the copper iodide. So what will be the expected product for these two? Here it will be participate in 1-2 addition.
1-2. 1-2,
And
yeah,
it will
1-4.
participate in 1-4. So here this will be my OH, double bond is intact. Here this is the incoming methyl group, and here will be what? Methyl group. Okay, this type of the molecule is going to be tasteless. And always remember, tertiary allylic alcohol is undergo the reaction with PCC. Reaction with PCC, that is called Babler oxidation. And Babler oxidation is going to convert that particular tertiary allylic alcohol into conjugated carbonyl. It's going to convert into the conjugated carbonyl. So look at the product now. Here, this OH is going to migrate at here, and this double bond is going to shift. This is the Babler oxidation. Only done on the tertiary allylic alcohol. So these are the two very simple examples where we are going to convert into the 1,4 and 1,2 addition like this. So write down some examples regarding that 1,4 and 1,2 addition. Okay, this is one molecule. So here the first example is very simple, and now the valency is exceed here. So we must omit one bond. Okay. Yes, this one. So this is going to convert into
1,4.
Okay, this one. And now here we are going to add the vinyl magnesium bromide, and vinyl magnesium bromide in the presence of copper, so it will be going to be add here. So it develop this molecule. Okay, and vinyl group is there. That means this will be here. So this is the chemistry of 1,2 and 1,4 addition reactions. Depend upon your type of reagent and type of what reactor now. If the crowding at alpha position, then 1,4 is there, and if copper is there now, so then it will be surely it's 1,4 addition. Now there is some question regarding the stereo selectivity. What about is the concept of a stereo selectivity? Now stereo selectivity means where if the crowding is there now, the where from the reagent is going to be attacked now. So let's take the example of the stereo selectivity. Suppose I have the cyclohexanone derivative now. And if there is a crowding at some position, so the specific molecule is this one. This is your molecule. Okay, and your reagent is going to attack from the top side or from the bottom side. It depends upon the your reactor. So here, if I'm going to add the reagent, that is methyl magnesium bromide. So here methyl magnesium bromide is always it is a nucleophile, and any nucleophile find the suitable route. So suitable route means what? So that route should be sterically free. That route should be sterically free now. Here, if we look the steric crowding of what particular this group is at above the plane. Here hydrogen also above the plane. Here hydrogen also above the plane. That means if this nucleophile is coming from this side, it feel the crowding of two hydrogen and one tertiary butyl group. And if it is coming from the downside, then it only feel the hydrogen. So basically, which will going to be the better route now? This will be highly crowded one because you cannot approach that nucleophile from the upside now. So the resulting product will be developed. This is for tertiary butyl group, and here this will be my OH, and this will be my what methyl group. But if the simple structure is given to you now, simple carbonyl compound is given to you now, then again there is a crowding is there now. The crowding is of one hydrogen and another hydrogen. This is the crowding, and this is what only one hydrogen is there now. Okay, and here my reagent is MEmgBr. Now in that case, resulting products either this one is coming from here or this one is coming from here. So it will be form two product. Here this will be methyl OH, and here this will be what OH and methyl. Now generally bulkier group should be on equatorial side. If it is equatorial side, that means this OH is on equatorial side, but this methyl is coming from upside. So in that case, the stereochemistry in that case what stereochemistry is decided by the stability of the product now. Okay, and that's why this will going to be the major product now, and that phenomena is called as a product development control. Here we are avoiding the such a kind of a crowding. Here very the small negligible crowding is there now, and we are avoiding it now. But in first example, we cannot avoid. We cannot avoid the crowding now because there are bulky group is there now, that is tertiary butyl. So that's why this OH is on top now. Basically, this product is unstable, but based on that steric approach control. So steric approach control means based on that stereochemistry, based on that particular crowding, we are decided the stability of the product. So these two examples are very important. Okay, in that case, this will be the major, where OH is coming from the upside and or axial position, or methyl is on the equatorial position. And in the last example, the methyl is axial and OH is what, equatorial. So this is called product development control, and this is called steric approach control. So we have also the similar example for the bicyclic molecules. Okay, now find out the product of two reaction. This is MgBr. So here in the first example, what there is a again crowding of one and one hydrogen here. This is the crowding of one hydrogen, and basically at the downside also there is a two hydrogen. The crowding is here. This is the crowding of only one hydrogen, and here this is the crowding of what, both hydrogen. So from where it will be going to react now? From the top side.
Okay.
From the what? Top side,
Okay.
it's going to react, and this will be my methyl group, and this will be my OH. Now in that case, the top side is what already blocked because of what, methyl group. So this will be the
Methyl
crowding is going to take place now. So it should be coming from the
group.
down.
Now.
So here this will be my OH, and this will be my methyl. So these are the two major products. No need to write the minor and etc. These are the two major products regarding this. One more example want to explain. That's for the Cram's rule now, and you know about the Cram's rule now, particularly in the what reduction family. We are already discussed that example. So whenever any chiral center is there, which is adjacent to which is what, adjacent to
Chiral center.
adjacent to the chiral center. Now here incoming reagent should be coming from the smaller group. Example, the chiral center first classified on the basis of their positions. So this is what the large group, this is what medium, and this is what the small. So here hydrogen is on the back side. So this reagent should be coming from back side. Okay, and resulting product is what, the your diisomer, and that will be the, and if the hydrogen or methyl group is coming from back side, so this OH should be on hydrogen,
OH.
methyl, phenyl, OH. This is methyl, and this is what hydrogen. Look at
Hydrogen.
the position. This hydrogen previously is the back side, and your incoming reagent also from back side. So this is the major diisomer is going to be developed. Okay, and that type of the reactions are called as a stereoselective reaction. So this is called a Cram's rule. Okay. Now we have
Yes.
various different molecules on which we are going to react the RMgX. Now, example, the reaction with ester, amide, acid chloride, acid anhydride. Okay, all are the same react. Example, we'll discuss about the acid ester now. RCOOR. This RCOOR is going to react with the RMgX. What happened now? So this negative charge from the R is going to react with this one. Bond first open to oxygen, bond closes to carbon, and OR is going to free now. So in the first step, it going to converts into the ketone. It's going to convert into the ketone. Further reaction with the RMgX. Further reaction with what, the RMgX. What happened now? Further reaction with what, RMgX. Again, the reaction will be very same, and the bond will be open to oxygen, so it will form the your product. This is R O negative. This is R. This is R, and finally the protonation will leads to the tertiary alcohol. Now, if look the reaction, conversion of ester, acid halide, anhydride, it needs two equivalent of the Grignard reagent to converts into the tertiary alcohol. If one reactant is going to be used now, it will be form only carbonyl compound as a ketone. And here tertiary alcohol is going to be formed by the application of second equivalent. Okay, remember this one. If one equivalent ketone is going to form, this is what, one equivalent. If second equivalent is added, then it will convert into the tertiary alcohol. The next example is what, lactones. Now you know that lactones are cyclic ester. What happened with this now? Lactones are going to convert RMgX. Now this R negative is going to react with the carbonyl carbon. Here bond will be open to oxygen. Bond will back to what, carbon, and this bond is going to free. This is called nucleophilic addition and elimination reaction. So here this will be a COOR, and here this will be what, O negative. Okay, like this. And by the protonation and by the, if we react further equivalent, one equivalent of RMgX, then that CO, that ketone group will also converts into the tertiary alcohol. Now this is what R, this is R, and here this will be the OH. So this type of the chemistry is there for particularly the lactose. This is what the lactose. So generally for ester, acid halide and anhydride, requirement of two Grignard reagent is there. Okay, what about the cyanide now? Which cyanide? When R scene is there, on react with one equivalent, what happen now? Look at this one. This Grignard is added onto the carbon, bond will be open to nitrogen. What happened? Next step, R C double bond N negative charge. This is what MgX, and here we are going to develop the new bond with the reagent, that is R. This is called imine salt now, and that will be going to convert, that will be going to hydrolyze, and it will develop the carbonyl compound. And this carbonyl compound is further going to react with the second equivalent of what RMgX, and it will, the next reaction, it will form tertiary alcohol. So one equivalent converts into the ketone, second equivalent converts into the next reaction with the what, carbon disulfide. That is what RMgX is going to react with carbon disulfide or carbon dioxide. What happened?
Acid.
The resulting products are carboxylic acids. Look at this one. This negative charge is going to react with the carbon. One of the bond will be open to oxygen. Next step. This is R, C double bond O and O negative
O negative.
MgX. So when it is hydrolyzed by the presence of what, H3O plus, it will be converts into the carboxylic acid. With the carbon disulfide, the resulting product is R, C double bond S and acid. This is called thionic acid. So carboxylic acid and thionic acid are the products are developed. Okay.
Yes.
So one question is for you. So if I suppose halobenzene, and halobenzene is going to convert into the methyl magnesium bromide. This is the first reagent. In the presence of our dry ether, you will get A, and on treatment with the CO2 with H3O plus, what will be the B? Okay, this is the question. So A is what? Your Grignard reagent, because it's not given. For here, basically what, this is what only
methyl bromide.
No, it is what?
Magnesium.
So magnesium is going to insert, and it will going to form a magnesium salt. That's magnesium X, and that will be going to react with the CO2. So it will form a benzoic acid. Okay.
Yes, sir.
Now what happened with the diester now? So when this Grignard reagent is going to react with the diester, what will be the reactant and what will the product is? Now look at this one now. If one equivalent is going to used, then it react with the carbonyl carbon, and first OET will be free now. The resulting product is what? This one. If we react with the next equivalent, that is RMgX, then one of the OET group will be again free. That will be ketone is going to develop now. And when this ketone is going to react with further equivalent of RMgX, then it will be form a tertiary alcohol. That means for a diester, the requirement is what? Three equivalent. Okay? Okay, this is what one, this is second, and this one is the third one. So now next example is what? The reaction with isocyanate now. Reaction with isocyanate. Now what is that isocyanate now? Here isocyanates are nothing but the R, N, double bond C, double bond O. When this compound is going to convert into the react with RMgX, what happen now? This R is going to react with the carbon. Okay, and more electronegative atom will take the electron, that is oxygen. So here this will be R, N, double bond C. This will be O negative, and this is what R. Now this molecule is undergo the protonation. Protonation will leads to converts into the R, N, double bond C. Okay, this one, and this molecule is participate in tautomerism. So here it will be form a primary amide. So how the primary amide is going to develop now? Look at this one. This is R, N, H, C, O, this R. This is called the, that means the isocyanate is going to convert into the amide. The last application is opening of epoxide. This is the again versatile reagent. Okay, opening of the epoxide. So you know that epoxides are versatile molecule, and that epoxide is going to open by the simple any nucleophile. Now, generally, what any nucleophile is responsible for the opening of what really this one, and RMgX is a self nucleophile, so it will open the epoxide, and resulting products are what the alcohols are going to be developed. Now, look at this one. This is what my R. This is what my O negative and something MgX, and finally by the protonation, it will convert into the product like this. But there is a reduced selectivity. Whenever we have unsymmetrical epoxide, we already learned this chemistry. Reduced selectivity in the opening of epoxide. Whenever we have the unsymmetric epoxide is there now, Grignard reagent is always open epoxide from sterically least crowded side because of what, like SN2 reaction. So this will going to be open like this, and here this will be the more substituted alcohol will be obtained. Okay, this is what the regio selectivity. And one more application example, we have cyclic epoxide is given. Now cyclic, you know that cyclic epoxide means cyclohexane epoxide derivative. First of all, that molecule must convert into the chair form. Example, this O is given on this side. Then what we have to do now? Always open the epoxide from axially. Axial opening is there now. That means this will be coming from here, and your resultant product should be the major one. This will be my OH. Okay, and here this will be the R. If I want to draw the structure in simple form, then here OH is on top side, and here R is on the down side. If any methyl group is given like this one, and here we are going to react with RMgX, then what we have to do now? Again, first draw the structure in the chair form. It will be easier to understood the from where we are going to attack. Okay, here look at this one. The position of methyl group is up. Position of methyl group is up, and this will be a downside. But from where we are going to react now? Again, from axial side, from any cyclic derivative or cyclohexane derivative, it should be from axial. And now axial position is only this one. Okay, and that means the resulting product will be, if I coming from this side, then your O will be here, OH will be here. Okay, now this methyl will be here, and this R will be here. This will be going to take place. And if you want to draw the simple form, then here this R will be at top, methyl will be at the bottom, and OH will be on also bottom. So this is the product of my desired reaction. If the same reactant is given, here methyl is down and this one is up, then what we have to do now? Again, what we have to draw into the chair form. Here methyl is down like this one. Okay, here something the chemist is there, and so you can easily attack it here from here. So resulting product will be this one, like this. So always remember, so opening of epoxide in this case will be what? Axial. So this is all about the your reagent that is called as a organomagnesium. So one of the widely used organometallic compounds for the purpose of making carbon-carbon bond.